rational functions, we want to find the things that we've been focused in class on finding, how to find asymptotes and different things like that. And in order to do that, it would be helpful to see a factored form of the equation. The numerator here does not factor. In the denominator, I can factor out a 2x squared, leaving another factor of x plus 2. So remember, as we're looking at things and reminders of how to find them, we want to look at asymptotes, intercepts, wholes. Okay, so first of all, for the wholes, there is none. I know that because remember that wholes are removable discontinuities. In other words, they come from factors that are originally in the equation, but then don't show up in the more simplified form, the factors that are canceled out. Here, no factor is canceled out, so there aren't going to be any holes in the graph. So now let's focus on asymptotes. There's vertical asymptotes, there's horizontal asymptotes, and there's oblique asymptotes. Okay? Remember, vertical asymptotes represent where the function is undefined. Given that the function is in a fraction form, it's going to be undefined when the denominator is equal to 0. Okay? So my vertical asymptotes are going to be found when 2x squared times x plus 2 is equal to 0. These are two factors multiplying each other set equal to 0. So 2x squared set equal to 0 would give me x equals 0. And x plus 2 set equal to 0 would give me that x equals negative 2. So I have two vertical asymptotes at x equals 0 and at x equals negative 2. On my graph, I would mark those with dashed lines like we talked about before. And we know that the vertical asymptotes are specifically representing where the graph would be undefined. It cannot cross those because those x values don't produce any y value. Next are horizontal asymptotes or oblique asymptotes. I say or because remember, we'll have one or the other. Both of these are different from vertical asymptotes. They are supposed to describe the end behavior of the function. If the end behavior of the function is horizontal, then we have a horizontal asymptote. If the end behavior of the function is not horizontal, then we have an oblique asymptote. And remember that we said we would decide this based on the degree of the numerator versus the denominator. In our function, the degree of the denominator is higher than the degree of the numerator. And that means that it is horizontal, specifically at y equals 0, based on what we discussed in class. And then that means there is no oblique asymptote. So we expect our function at the ends. I don't know what's going to happen in the middle. It could cross this, it might not, whatever. But at the ends of the function, I expect it to even out at the line y equals 0. So we've discussed wholes and asymptotes. For intercepts, so remember, to find an x-intercept, we're basically setting y equal to 0. Okay? But remember, when y is set equal to 0, in this case f of x is like our y value, we have 0 set equal to this fraction, which is going to happen every time since we're dealing with rational functions. We're going to have this fraction. The denominator is not going to contribute to the y-intercept because in order to solve this equation, you're going to multiply both sides by that denominator to cancel that out. And on this left side, it's always just going to become 0. So we talked about recognizing in this fraction form that an x-intercept could be found by setting that numerator equal to 0. And in this case, if I solve this equation, I get x squared equals 1/2, square root both sides. So I get x equals plus or minus 1 over the square root of 2. And if you rationalize that denominator by multiplying the top and the bottom by rad 2, I'll get that x equals plus or minus rad 2 over 2. To help us out here, if I'm not going to let you use on the calculator on the test, I wouldn't expect you to know exactly what rad 2 over 2 is. You could still estimate it because you could estimate the square root of 2. But it's basically 0.707. So we'll use that in a minute. Because remember that x-intercepts aren't just x-intercepts, but they are points on our graph. They have meaning for us. We can plot them and find them and use them to help our graph. So our x-intercepts are going to be at plus and minus 0.707. And then we also need to find our y-intercept, which remember is found by taking our function and solving for y when we plug 0 in for x. You can see you're going to get a 0 in the denominator, so it doesn't really matter that the numerator is 1. This is undefined, which means there is no y-intercept. That makes sense when we look at our graph, because remember we had a vertical asymptote at x equals 0, meaning there wouldn't be a point there. So right now we know 2 points on our graph that we have at positive 0.707 we have an x-intercept, and at negative 0.707 we have an x-intercept. Now, just take a moment to think about graphs, and we're going to use a sign chart next to decide where the graph goes. So we're going to focus on not plugging in and plotting points, but instead drawing the curves in their appropriate location based on how we know the function will behave. So real quick, I want you to recognize that let's say you have your x and y axis. Remember that the y value is above the x-axis and negative below the x-axis. Okay? So here and here. And let's say this function so notice that I'm going to outline in green, the places where the function has a positive y value. So here and until we get to here, up here until we get to here, and all up here. And then I'm going to outline in red where the function has a negative y value, and that would be from here downward and from here downward. So notice the only places where the y value could change from positive to negative. So it was positive, and then it hit this point and changed to negative. That's an x-intercept. Then it hit this point and changed negative. That's an x-intercept. Okay. But notice, once I went over to the other side of this asymptote that's right here, it was positive. So it can also change whether it's positive or negative on each side of a vertical asymptote because it's not connected. So the places where it's going to change from positive to negative, if there is any change, are going to be where there's vertical asymptotes or where there's x-intercepts. Okay? So knowing that, I'm going to go back to the graph we just looked at. And I'm basically going to think about a number line that represents the x-axis. And I'm going to think about all the places that the function could change directions. So there's a vertical asymptote at negative 2. There's an x-intercept at negative 0.7. There's another vertical asymptote at 0, and another x-intercept at positive 0.7. So in between those, the function could change from positive to negative. And how do I know it's going to happen? I'm going to plug a number into my equation. So for stuff less than negative 2. Okay? So for stuff over here, what's happening? Is the curve above the x-axis or is it below? Okay, are the y values positive or are they negative? I would plug in some number like negative 10. Okay? So I'm thinking about what that looks like when I plug it into this function here. And when it's factored, it's nice to think about each group and whether it's positive or negative. And what I mean by that is I'm going to think about this is one factor up here, so that's a group. And then in the denominator, I have this set and this set. Okay? So what I'm seeing is this positive or negative? Is this positive or negative? Is this positive or negative? And what's going to happen when I multiply them all together? So in the numerator, it would end up being negative. And in the denominator, this factor would be positive and this factor would be negative. So I would have a negative in the numerator. In the denominator, a positive times a negative is still negative. And when the negative in the numerator is divided by the negative in the denominator, I expect the outcomes in this area to be positive. Then I'm going to do the same thing over and over again, but think about plugging in different numbers in those spots. Okay, and for this first example, I'm going to show each number that I'm plugging in, and for the further ones, you should be able to try it. So between negative 0.7 and negative 2, so I'll try negative 1. Okay. Again, in the numerator, I still get a negative. In the denominator, this is still a positive. Okay. And negative 1 plus 2, that will be a positive. Okay. So my denominator is positive, my numerator is negative, so they're going to be negative in there. Okay. Between negative 0.7 and 0, let's say I plugged in 0.5. Negative 0.5. So if I plug in negative 0.5, the denominator still has two positives multiplying each other. And in the numerator, let's see, negative 0.5 squared would be positive 0.25 times negative 2 would be negative 0.5 plus 1 would be positive. So these would all be positive. So this would be positive. Okay. Then on the other side of the asymptote is 0, so let's say between 0 and 0.7. So let's say now I want to plug in a positive 0.5. If I plug in a positive 0.5, I'm definitely getting positive values in the denominator. And in the numerator, I'm again getting a positive, so this will be positive. All right, so then if I plug in something larger than 0.7, so say like, it doesn't matter, 1, 10, okay? Just for simplicity, I'll plug in 1. Then I'm going to get two positives in the denominator still, but a negative in the numerator. And then if I multiplied or divided that out, my answer would be negative. All right, so what does this mean? This means my function is completely positive or completely above the x-axis. All the y values are positive on the left side of the asymptote at negative 2. So given that I have asymptotes here and I know the end behavior has to follow this and it's going to rise up along the asymptote, and I know that it stays positive and there's no x-intercept there, that would be my estimate of a curve there. Then from the asymptote to the x-intercept at negative 0.7, everything is below the x-axis. So again, given that you follow an asymptote, you're either going to be here or up here. I know it's not up here because it says it's going to be negative, so I know it's here along the asymptote. And I know I have to come up to that x-intercept. Okay? Then from that x-intercept to the next asymptote, everything is positive. All the points have y values that are positive, so it's above the x-axis, so it must follow up here. Then between that asymptote and the next x-intercept, I have positive, so again, it must follow the asymptote up here, but I know that the curve has to come to the x-intercept. After that x-intercept, everything is negative, so I know it's going to go below horizontal asymptote for end behavior. X-intercept and it doesn't go back up positive, I know it's going to follow like this, which means it must come down here and then just kind of like come back to the asymptote somehow. Excuse me. All right. So that's what we would say our example is. And then if we listed the domain and the range, the domain for this function, you see the only x values you can't plug in are where your asymptotes are. So we would just say that x cannot equal 0 or negative 2. And the range for this function, just given this center section right here, the fact that the curve goes infinitely upward and downward, the range would be all real numbers. All right, so next example. Okay, So again, the first thing I want to do is I want to factor it so that I can see what's going on with the function. Okay, so I have a lot of factors here. Nothing cancels. So again, what does that mean? That means that there are no holes. Then for vertical asymptotes, horizontal asymptotes, or oblique asymptotes. For vertical asymptotes, remember what makes the denominator equal to 0? So if my denominator has the factor 2x plus 1 and x minus 3, if I set those equal to 0, I'm going to get two vertical asymptotes, one at x equals negative 1/2 and one at x equals 3. Mark those on the graph, and then again we're going to choose. There's not going to be both horizontal and oblique asymptotes. There's going to be one or the other, and that's going to be based on the fact of the degrees of the numerator and denominator to determine how that function grows. So when I look at this function, if I had multiplied everything out, the degree in the numerator would be the same as the degree in the denominator. Like this would say 3x squared minus 3x. So remember, when the degrees are the same, we're focusing on both of the first terms here, and we're using the ratio between the lead coefficients. So in this case, 3 over 2. So there is a horizontal asymptote, and it's at y equals 3 over 2. And then that means there is no oblique asymptote. So at 1.5, which is 3 over 2, I have a horizontal asymptote. So then for my intercepts, again, for my x-intercept, I can focus on the numerator. So I'm going to think, okay, if I take 3x times x minus 1 and set it equal to 0, I'm going to get two possible x-intercepts, and that's going to be at 0 and at 1. For my y-intercepts, I'm going to plug 0 in for x. And when I do that, let's see what this looks like. I have 3 times 0, 0 minus 1, 2 times 0 plus 1, and 0 minus 3. And so here I'm getting 0 in the numerator, and negative 3 in the denominator, which is just 0. So my y-intercept is at 0, 0. Shouldn't be too surprising based on our x-intercepts. Okay, so I'm going to go ahead and plot all of that information on here. So I have x and y-intercept at 0, 0, and I have another x-intercept at 1, 0. Okay, so let's look at what's happening with our sign chart, and then we'll come back and do our domain and our range. So remember, with our sign chart, we're basically thinking about the x-axis and places where the function could change from above to below. And that's at vertical asymptotes, which we have one at negative 1/2, or at x-intercepts. We have one of those at 0, one at 1, and another vertical asymptote at 3. So we want to evaluate our function in these intervals and see whether it's positive or negative. Okay? So again, what I'm doing here is I'm thinking about this function, and I'm thinking about when I plug a number into that 3x, when I plug a number into x minus 1, 2x plus 1, and x minus 3, if they're positive or negative. So the first section I'm going to look at is numbers smaller than negative 1/2. So like, let's say I plugged in negative 10. 3 times x would be negative, x minus 1 would be negative, x minus 3 would be negative, and 2x plus 1 would be negative. If I calculated that out, multiplied and divided, it would end up being a positive. Okay? Then between negative 1/2 and 0, let's say I plugged in negative 0.2. Okay, 3 times x would still be negative, x minus 1 would still be negative, x minus 3 would still be negative. Negative 0.2 times 2 would be negative 0.4 plus 1. This would be positive. So my overall result would be negative. Between 0 and 1, let's say I plugged in 0.5. So So this would be positive, this would be negative, this would be negative, and this would be positive. So overall here I'd get a positive. A number between 1 and 3, let's say I plugged in 2. This is how the distribution would look, which would make the multiplication and division negative. And then finally, if I plugged in a number larger than 3, all quantities would be positive, giving me a positive. So in this first section right here, any x value plugged in smaller than negative 1/2 produces a positive. Now, I know that my graph either needs to follow the end behavior here or here, and it either needs to go up along the asymptote or down. It can't go below because it would have to cross through the x negative. So I'm going to kind of assume that the curve must be there. Okay? All right, then from the asymptote, and again, it's either going to be up here along the asymptote or down here along the asymptote. But it says that right after negative 1/2, it's negative. It must come up and hit the x-intercept. But then after the x-intercept, it's positive, so it goes to the asymptote. But then must come back down to hit 1. So goes through the asymptote, but must come back down to hit the x-intercept at 1. And after that x-intercept, it goes negative. And the next thing we have is an asymptote, so I take it to eventually follow that asymptote. Okay. Then on the right side of this asymptote, it's either going to follow it down or up, and at the end behavior, either above or below. Given that in my sign chart, positive, I'm assuming it must be this curve right up here. Okay, so there's my graph. So I would come back to say the domain, which in this case, again, x just cannot equal where the asymptotes are. So here are negative 1/2 and 3. Now for the range, kind of depends on how you drew it. Behaviors get closer and closer to 1.5, but don't necessarily cross. And then I drew my parabola up to 1. I'm not making you guys plug in and check, so I would have to accept, whatever you write. So based on my graph, I would say that y is greater than 3/2, or y is less than or equal to 1. All right, let's get another example. Okay, so in this example, everything's basically factored, so we can get right into assigning things. So no factors cancel, so we don't have any removable discontinuities. Okay, we don't have any holes. Okay. Then we want to look at our asymptotes. So the vertical asymptote, in this case, the denominator is x plus 3, or 3 plus x. So we're only going to get one place where there's a vertical asymptote at x equals negative 3. Now, for horizontal and vertical asymptotes this time, the numerator has the higher degree, which means there is no horizontal asymptote. So now we have to look for, the oblique asymptote. And to find the oblique asymptote, we literally have to do division of the problem, okay? So if I do division, and you could, in this case, do synthetic division, but if it wasn't x plus 3, you'd have to do long division. So 5x would be the first thing I would choose. It would give me 5x squared plus 15x. Remember that we're really subtracting all this, so these cancel. I get negative 15x plus 0. So the next thing I would add is a minus 15, and when I distribute that through, I get negative 15x minus 45. But again, remember, we're actually subtracting, so the signs will change. So when I divide, my quotient is 5x minus 15 plus this remainder of 45 over x plus 3. Okay. However, for our oblique asymptote, when we look at this, okay, if we plugged in really big numbers for x, this fraction would basically get really, 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 really close to 0. So this part of the equation is going to determine what the function will behave like at the end. So the oblique asymptote is going to be 5x minus 15. So I'm going to renumber my graph by 5s just for simplicity's sake. Okay, so if I graph 5x minus 15, 10, 15, negative 15 is the y-intercept, and the slope is So up 5 over 1, or up 25 to go over 5. So 5, 10, 15, 20, 25, 5, 10, 15, 20, 25, 2 over 5. And I had a vertical asymptote at x. And then I got to finish finding the rest of the stuff. So x-intercept is going to occur when 5x squared equals 0. So that's when x is 0. So I expect an x-intercept at 0, 0. My y-intercept is going to be plugging in 0 for x. And I get 0 over 3, which gives me, again, 0, 0. So I have this intercept. So I'm going to go do my sign chart. There's a vertical asymptote at negative 3, and there is an x-intercept at 0, and that's it. So when I plug in something smaller than negative 3, in this case, the numerator is always positive because x is squared, and in this case, the denominator would be negative, so this would be negative. Between negative 3 and 0, like something like negative 1, that would be positive, so it'd be positive. And then if I plug in a large positive number, it's still positive. Remember, the fact that the oblique asymptotes are here means your function needs to follow these at the ends, either there or there. Okay? So, don't copy this part down, but I kind of see two ideas. Either my function follows these asymptotes like this, or it follows these asymptotes like this. Okay? Given that this says it has to be all negative and no x-intercept here across, use this portion down here in that little curve, and I'm going to erase this other part that doesn't fit what our sign chart says. Okay? So on the other side of the vertical asymptote, so it followed it down here. On the other side, it's either going to follow it down here or up here. It says positive, so it must be up here. Okay? But I know it has to come down to this x-intercept at 0. But then it says positive again, which means it doesn't cross all the way through. It goes back up. So I'm going to turn it back up, and it's going to follow that axis. Okay? So our domain here, again, x just cannot equal negative 3. And our range, again, because we're estimating, is a little bit, you just have to use where you've plotted the points. So y is definitely greater than or equal to 0. Or, let's say I had this curve right here, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, negative 9. Y is less than or equal to negative 9. All right, another example. All right, so again, I'm going to start with factoring. Those cancel. So I'm really just left with a really simple equation. Really, I'm just left here with y equals x minus 2. That's a line. Okay, that's really easy. But let's talk about these things here. As far as holes, we found one. Okay, x plus 2 is a factor that was canceled. So there's a hole when x is equal to negative 2. And then we'll talk about where that actually is on the graph. Okay? Then as far as vertical asymptotes, there isn't any because the one factor that would have made a vertical asymptote was actually contributing to our hole. So it's a removable discontinuity instead of non-removable. Horizontal asymptote, there is none because the degree of the numerator is higher. Oblique asymptote, you've already simplified and divided it out. It's kind of weird. Is itself, it's just going to follow this line. You might be able to write none there. Then for x-intercepts, I'm going to take this simplified version of the equation and set y equal to 0 and get that x is equal to 2. So I expect it to cross at 2, 0. And for y-intercepts, I'm going to plug 0 in for x, which gives me the point 0, negative 2. Now, if I just plotted this function, I am just plotting whose x-intercept is positive 2, 0 and y-intercept is negative 2, 0. So there's our line. The only problem with this is there is a hole. You have to account for the fact that in your original equation, there was this denominator, and if you put -2 in there, the value's undefined. But on your graph, what you're showing me is if you plug in -2, you're getting this point right here. Well, really that point doesn't exist. That's where your hole is. Okay, so you have to literally go to your graph, and we're going to draw it with that point missing. So to do that, we just make an open point like that. And there's our hole. Okay? So the domain is that x cannot equal -2, that one place where the hole is. And the range, notice it's a line, so it's all real numbers, except for it is missing this y value right here of -4, where it would be at -2. So y cannot equal -4. All right, next one. So we have x minus 5, x minus 5 times x plus 3. These cancel, and we have 1 over x plus 3. Okay. So again, we just identified a hole or a removable discontinuity whenever x is equal to 5. The vertical asymptote is going to be at x equals -3 because that's when the denominator would equal 0. The horizontal asymptote is at y equals 0 because the degree of the numerator is higher. And then there is no oblique asymptote. Okay? For x-intercept, if I set y equal to 0, and I multiply both sides by x plus 3, I get x equals 1, which is not true, so there is none. And for my y-intercept, so y is equal to 1/3. So I have a y-intercept at 0, 1/3. I have my x-intercept, and I have my asymptotes. And I mark those on there. Okay, so again, to do my sign chart here, I'm really just concerned what happens to the left and right of -3 where my vertical asymptote is. And I don't have any x-intercepts, so that's it. So I'm going to take this simpler function. When you plug in a number smaller than -3, like -10 to that function, the value will be negative. When you plug in something bigger than -3, like 0, the function will be positive. Okay? So the function exists entirely down here on this side of the asymptote with negative y values, and then entirely up here on this side of the asymptote when there's positive y values. So the domain here is everything except x cannot equal -3. And the range, since it doesn't hit that line at 0, is that y would not be equal to 0. Now, actually, I need to add a couple things to that because this graph was supposed to have a hole at x plus 5. So right here should actually be an open point on our graph, which means x can also not equal 5, and y can also not equal whatever you get for y when you plug in 5, which is 1/8. All right. The last examples are for you guys to write an equation. I want you to try and write one and bring it to class with you tomorrow. That's how I'll know if you followed the directions on them.